The idea that an AI model like Claude can function as a user space internet protocol stack is a fascinating technical claim that has circulated through engineering circles. But the real problem here is not just whether the claim is true, but what happens when you try to build a production system on top of it. If you treat a large language model as a network protocol, you are not just adding latency, you are introducing fundamental architectural incompatibilities that break the very foundations of how network communication works. By the end of this explanation, you will understand why the absence of performance data for this specific use case is not an oversight, but a critical signal that this approach is fundamentally non-viable for real-world infrastructure. To understand why this concept is problematic, we first need to define what a user space internet protocol stack actually is, in a traditional sense. In a standard computer, the internet protocol stack handles the movement of data packets between your device and the rest of the world. It operates with deterministic rules, where a specific input always produces a specific output in a fraction of a second. When engineers talk about moving this stack into user space, they usually mean running the networking logic as a regular application, rather than inside the operating system kernel, which allows for greater flexibility and customization. The promise is that you can build custom network behaviors without needing deep kernel-level access. The hype around using a large language model like Claude as this stack suggests that we can replace the deterministic logic of a router with the probabilistic reasoning of an AI. The implication is that Claude could receive a network packet, analyze it, and respond with the appropriate routing decision or data payload. This would theoretically allow for incredibly smart, context-aware networking that could adapt to complex traffic patterns in ways traditional code cannot. It sounds like the ultimate evolution of network intelligence, where the network itself becomes an intelligent agent rather than a dumb pipe. However, the moment you try to apply this to a real ping operation, the physics of the system immediately reveal a massive disconnect. A standard internet ping measures the round-trip time for a small data packet to travel to a destination and back. In a traditional network stack, this process takes milliseconds, often just a few milliseconds depending on the distance. The entire system is built on the assumption of near-instantaneous response times because the logic is compiled, optimized, and running directly on the hardware. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. When you attempt to route this same ping through a large language model, the latency floor explodes. You are no longer dealing with simple bitwise operations or lookup tables. You are triggering a massive neural network inference process. This involves sending the packet data over a network to a remote API, waiting for the model to load its context, processing the request through billions of parameters, generating a response token by token, and then sending that response back. Even with the most optimized local inference setups running on powerful hardware, the minimum time required to complete this cycle is measured in seconds, not milliseconds. Research into related tools, such as the usage window management scripts for Claude, shows latency figures in the range of 2 to 5 seconds just to trigger a command. This is not the latency of a network protocol. This is the latency of a slow, asynchronous controller. If you were to try to use this for actual network routing, the system would time out long before the model finished generating a response. The standard timeout thresholds for TCP connections are set to handle network congestion or slow servers, but they are not designed to wait for an AI to think. The result is a cascading failure where the network stack appears to hang, forcing engineers to build complex watchdogs just to detect that the system has stopped responding. This brings us to the core architectural mismatch. An internet protocol stack requires a persistent, low-overhead connection state. It needs to know exactly where every packet is at every moment. Large language models, by contrast, are fundamentally stateless in their inference process. Each request is treated as a new event, requiring the model to reevaluate its context from scratch. This means that for every single ping, the system has to reload its entire understanding of the network state, incurring a massive computational overhead. There is no persistent connection state to maintain. The model cannot hold a conversation with a packet. It has to restart the conversation every time a packet arrives. The community has tried to work around this limitation with features like cache refresh pings and heartbeat mechanisms, but these are application layer fixes for a protocol layer problem. They are essentially band-aids that try to keep the session alive or prevent the model from timing out, but they do not solve the fundamental issue of speed. These workarounds prove that the system cannot natively maintain the continuous, low-latency state required for a protocol stack. Instead of being a fast, synchronous data plane, the model becomes a slow, asynchronous controller that sits behind the network, adding layers of indirection that degrade performance rather than enhance it. The most valuable insight here is that the lack of empirical latency data for this specific role is not a gap in the research, but evidence of the concept's failure. If this were a viable architectural pattern, we would see benchmarks comparing millisecond-level kernel performance against second-level model performance. We would see case studies of companies deploying this in production. The silence on this front tells us that the engineering community has recognized the flaw. The user space IP stack narrative is a conflation of distinct technical concepts that do not actually work together in practice. Treating an inference engine as a network stack introduces architectural inefficiencies that cannot be optimized away. The probabilistic nature of the model means that responses are not deterministic. In a network, you cannot have a router that sometimes says, "send this packet," and sometimes says, "drop it," based on a probability distribution. The network requires absolute certainty. The overhead of context switching and token generation creates a system that is unreliable and non-deterministic, making it unsuitable for any critical infrastructure. The reality is that large language models are incredible at processing natural language and generating creative text, but they are terrible at acting as a network protocol. They are too slow, too stateless, and too unpredictable for the job. The novelty of the concept is undeniable, but the architectural viability is non-existent. Practitioners should recognize that the usage window management patterns and API heartbeat mechanisms are signs of a system struggling to function, not a new paradigm in networking. The gap between the hype and the reality is not just a matter of optimization, it is a fundamental mismatch between the nature of the technology and the requirements of the task. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.